Thank you very much. Good morning all. So I'm pretty happy to be here, to make a presentation following up of what we presented with Daniel last year, and that was why do larvae hatch when they do. So I start by something very easy for all of us, I guess, that hatching means the exact moment when an individual, usually called an embryo, will leave his egg envelope to become something free, which is usually called a larvae. So basically, when you want to work in hatching, there's not a lot of many people actually that work on that, because usually they will consider it not really interesting. Because it's considered as a simple phenomenon. You have an individual within an egg envelope, and then it's free. So basically, that's the main reason why, to our best knowledge, nobody really has this question. Why do fish larvae hatch when they do? So that's the first reason. Nobody really cares. The second reason, so in the past year, I asked this question to like dozens of students, colleagues in Congress, and so on, and say, that's a pretty dumb question. The answer is so easy. When they're ready. That's the answer that most people, either they don't care, or the other reason is that. But actually, it's really interesting question, because if you really want to tackle this question, you have to think about biology. And I really advise you to read this very good article by a colleague and a friend, Guillaume Lecointre. And actually, what he says, so Evo, you can replace that by biology. Incorporate into his research program idealistic views where order and regularity are the cause of biological phenomena. Things are at the right place, and the order to come is already written. So usually it took me a while to understand those sentences. So basically, what does it mean? It means that we know natural selection and so on for individuals and species and so on. But it's exactly what happened within individuals. But what replaced that up to now is the genetic program. So actually, what we think, or most people think, is that they hatch when they do because it's in the genes. So basically, if you do think like that, this is the kind of sentence that you will find in most introduction. Upon the hatching of teleos embryos, the egg envelope is digested by enzymes. What do you explain here? Nothing. It's just tautology. So, well, you have to find something else. You have to find a trigger. And that's where we discussed with Daniel. So there was wonderful presentation before, so I don't have to explain anything about gold. But actually, the idea here was just to apply gold to early life stages. So that was a basic idea. So you have an embryo, one cell, it will develop, and at one moment, so it's the guy on the right, it will become a larvae previous to hatching, and his needs will no longer be coped by the oxygen that diffuses through the eggs. So he has to hatch or die due to asphyxia. So here, it might appear a very simple idea, but actually we made three main assumptions. The first one is that during this development, it's only diffusion of oxygen. So you have a small eggs, you have oxygen all around, and this oxygen will go within the eggs. So it's only diffusion. So what matters here is the size, of course, of the eggs. So the larger eggs, more oxygen can go through. The second assumption is that, and it's different from what was presented for adults, is that for larvae, those are really different because the entire body is involved in respiration. So it's really different from what was presented. And there's very tiny, not a lot of articles that have done that, but Rambo did a wonderful work. So he looked at 7 parts in the entire body, and each part is involved in respiration. In other words, the larger larvae, the larger surface, so the more oxygen they can get. The third main assumption is that, okay, if we're saying that at one moment in the development, in hatching, they have to hatch or die, it means that the peak of oxygen must be at hatching. And actually, this is exactly what happens. So in this graph, on the left, you have the oxygen consumed by the embryo, and at one moment, he has to hatch, it's his peak. And then what happened is really nice, because it continues. Why? Because he can now breathe with his entire skin, but no egg envelope anymore. So that's where he can continue. So with the three main assumptions, this is what we have done. So we look at the egg diameter to calculate the surface, and we look at pictures and drawing and so on to try to have as more as possible the surface of larvae at hatching. So thanks to Charles and Elaine, we were able to get information for 33 species. And so we have egg diameter that range from 0.6 up to 5.7, and larvae from 1.1 to 22. This is a very low number of species, but we still have a large range of egg diameter because most eggs are actually below 2 millimeters. And yes, so we did not take into account any biology of the eggs here. There are small eggs, big eggs, but they have eggs, with different kinds of stuff on it. So we don't take anything here, or the temperature where it incubates, tropical, and still we have a trend that is really strong. So any species will hatch when its larval surface is 1.5 of the egg surface. In other words, what triggers hatching is when this ratio, whatever the species in this world, is reached. So not larvae, but each individual will hatch when it does to avoid asphyxia. So that's the trigger. And it will trigger two main things: mechanical process, so the behavior, so they have not enough oxygen, so they have to move, to find oxygen. That's the main mechanisms. And the other one is that they will produce enzymes to digest. So we can sum up what I said here. So as you see, there's different eggs, and they're not hatching in the same time. So it's each individual. Okay? So each guys, at one moment, they will say, oh, I got to hatch, or I will die. And what is really funny here is if you see the pectoral fin, of course they will not swim with that. This seems out of breath, It's at the end there you will see, the on the top. Pectoral fin moving very fast, and you have the feeling that, it's like out of breath. So, it's probably the reason why. Okay, what's next? Well, we will continue to do that, and there's many assumptions or many things that we can do. So, for instance, we're pretty confident that for the same egg size, fanning should provide more oxygen. So we do expect that for the same egg size, larvae should be larger at hatching. Oh, the other thing, I'm smiling because in the past month, I have to talk to colleagues working in physics, and I'm really bad in math. So I cry all the time, but still, we were able to have students. And basically, what I love with those questions is a matter of biology, but also physical constraints. And when you talk to physics, they understand that and they put that in equation. So we will continue to do that. And the last thing that we would like to do is actually we can do pretty easily now some experiments. And usually, or 99% of the time, when you talk about global warming, people will work on what? Temperature. But actually, when you work on temperature, you also work, but you don't think about it, about dissolved oxygen. So now what we want to do is not to change temperature, but only dissolve oxygen. So by doing that, and also we can measure, here you have the expression of the enzyme that is produced to digest egg envelope. When you combine those, well, you can look at the mechanical process. So I'm expecting that for the same temperature, if you decrease prior to hatching the oxygen, those guys will move much more and they will produce these enzymes. Thank you very much for your attention.